Ladies and gentlemen, this is Anton Vermelt's and Kevin Colleen's independent lab on magnetic strength. Right off the tip of the bat, the purpose of this lab was to calculate the magnetic strength of various magnets by measuring the force and distance between the two identical magnets. We had a lot of ways. We had to do some research independent of the lab on like the internet and whatnot to find some equations that would help us calculate this. There's a boatload of equations for magnets, as we found out. Anton's writing a few of them down. We chose the simplest one. We'll get into that later. We hypothesized that if we measure the forces between various magnets, then the attractive force will be equal in magnitude to the repellent force for each individual pair of magnets. Does that make sense?
Yes.
It seems like it should make sense. We'll talk about that later, though. We also hypothesized that if we calculate the magnetic strength of various magnets, then we will find that we call them the devil magnets. They're actually those magnets up there. These things are wickedly strong, and like if you literally even stick them together, they're impossible to like take apart. So they're like the devil. So those are really strong magnets. That was pretty simple. We just said that they'd be stronger than magnets that suck. The equipment that we used, you had to make sure you had a pair of identical magnets. It's important that you had identical magnets. We used low friction carts and a track. The force sensor thingy. We had to have string, lots of tape, distance sensor, computer cables. You guys know the drill there. Here's a few diagrams. So what we did, starting with this one, we basically set it up so they had magnets on either end of the cart, and right here, can anyone tell me if this would be an attractive or repellent system? Are these magnets going to be attractive or repellent? Just based on, bingo, attractive, because it's going to want to pull this guy away from the force sensor. So and then here's our distance sensor. As we pushed them closer, we measured the force. Does that make sense? Here's a little up close portion of how we did the force sensor. The string came in handy there. And then right here, this is when the magnets were repellent. So as we pushed them closer, then it would push against the force sensor, and we could measure the force that way. This is an up close of how we had to do a ton of tape with the magnets, like a good amount of tape, or else they'd like separate. It was really frustrating because once you get super close, the magnets would typically just go towards each other, and it's tough. Procedures, pretty straightforward. I'll read it to you guys. We collected the equipment and set up the experiment as shown in the diagram. Here's a little pre-lab warning. Some magnets are very strong, so be sure they never stick together. It helps to wrap them in paper or something, and it hurts when you get your fingers pinched. First, collect the attractive force between two magnets. Be sure that the magnets are nearly identical and that they are facing each other with opposite poles. Use the string. Attach cart 1 and the force sensor so that the sensor will read the tension in the string, which should be equal to the attractive force. Does that make sense? That's how
pulling on the string, so that's how we recorded the force with the force sensor.
Bingo. Keep cart 1 in the same position and record this position. Start from a distance that gives 0 force, and then slowly move cart 2. We talked about this. This is pretty straightforward.
And did you talk about the position sensor we use?
Yeah.
Okay. Same thing for repelled, except pushing against the force sensor, like Kevin said. Yeah. And so I guess technically we got a negative force for that.
Yeah.
So we just multiplied by -1 to make the graphs more clear and stuff for us.
And then once you have this, step 6, once you have the attractive and repellent force graphs and the consequential position graphs for various magnets, do graphical analysis to calculate magnetic strength using the equation on the following page. Note that your position graph is not equal to the distance between the magnets, so adjust it until it is. If possible, compare your results to the theoretical or calculated accepted values. So we just took some raw data about the masses of the magnets,
Some of the crazy equations in there.
yeah. And also, for some of the equations called for the distances from the poles of the separate magnets. So like the distance
Inside the magnet itself.
inside the actual
Which is-
magnet. Here's a couple of equations. So some equations were dependent upon the area of the magnet. This is like an equation for like force of a bar magnet. This equation is like force of a cylindrical magnet. I don't know. IDK. Here's this is the one we used. This is for point magnets, which that looks a lot like our friend. Does anyone know? Does that look familiar?
Point charges.
Yeah, it looks like for
Like electric
electricity
force
or
and
even
magnetic.
gravity. Yeah, so that's, I guess that's a pretty,
And we used Q
General
as magnetic strength
yeah.
of the magnet.
Q here is magnetic strength.
And that's where it becomes important that you use the same magnet, because you can assume that the magnetic strength of each magnet is the same. And so you can make that into Q squared, and that way you can solve for Q.
Just with the simple root.
Kind of like the electron, the pith ball lab. We'll take questions at the end.
So here's explaining that equation again.
So yeah, this is just algebra solving for magnetic strength, and then you want to go to the.
Yep. So then here's our graphs. As you notice, as the distance between the magnets gets smaller, the force gets greater.
Until eventually it peaks and they stick together.
Yeah. And that's where it got
Which we
pretty
kind of tried to
vicious.
avoid, yeah.
Yeah.
And then, so our graphs, the linearized graph, we used, like our linearized data, do you have it written down there? Is the square root of mu over 4 pi r squared, and we put that on the x-axis, and the y-axis we rooted the force, and so our slope came out to be root f over root of mu over 4 pi r squared, which equals magnetic strength. And we did it for the different magnets and the repellent and attractive forces.
This is
Same kind of.
So, yeah, this is cool. This is comparing the repellent forces. This is the attractive forces of the devil magnets. This is for the Pasco carts. So those carts that we bought, they have magnets within them. So you can do cool stuff with those carts.
And that's
if
what
they've
you
got
would use
magnets.
for the, what would it be?
For,
Perfectly inelastic? I don't know.
yeah, something like that.
Something like that.
Yeah.
Elastic?
So based on the slopes of these
Elastic.
linearized
Elastic?
graphs, at the end we were able to conclude that the devil magnets had an attractive magnetic strength of 838.9 amp meters and a repellent magnetic strength of 1516 amp meters, 1516 amp meters if you want to call it that. And the Pascal cards had a repellent magnetic strength of 475 amp meters. That we found it odd that the attractive and repellent magnetic strengths were so different. This will be discussed in greater detail in our conclusion. Let's cut straight to the. We'll talk about sources of error. Yeah, basically, sources of error were rampant in this lab. Our system wasn't quite perfected when we started, so it took a bit of trial and error before we felt we could take some real data. And after working out the kinks, we still had some definite error.
Using such strong magnets, like these magnets are really strong, and that makes it difficult because you're trying to get the force to increase at a constant rate, and you're trying to move it at a constant rate, but they're really pulling hard against each other. And even like with one strip of tape, it'd tear the tape off and attract to each other. So, and then that's a new process of trying to get them separated.
Perhaps what could have been most detrimental to our lab is the possibility that we could have used the wrong equation. Because there were so many different magnetic equations, we assumed each one had like a different level of accuracy,
Yeah.
but this, I mean, going back to those equations, this is literally the only equation we could use. And the thing about this equation, though, is you have to treat Q as a a point magnetic charge. So it's literally just like a single point, which we had like a whole magnet. It's really difficult to get like just a
A field
single
line, yeah.
point of magnet.
Ideally, those other equations would have been more simple, and we could have tried to use different ones and compare them to see which one may or may not be more accurate. But those were a little intense for our independent lab.
For our air analysis, we compared the attractive and repellent forces, because we assumed that would be the same initially between the two magnets. I don't see a reason why not. Can you guys think of anything? We really thought on this one for a while.
Repeat the question
More
one more time.
potential whenever they're repelling, maybe?
Why the repellent and attractive forces
Would
could
be
be
different.
different between the two magnets. It's a brain teaser.
Maybe if they're repelling, there's more potential because they can go farther away. I'm not sure.
Yeah, the distance could be greater
Yeah,
between
they could,
them.
I mean, but I don't know if that would have anything to do with it.
I don't know. I feel like he's on the right track.
That could make sense because
Maybe
R squared's in the numerator
I mean,
of
well,
this,
technically, if it was
so a bigger R. would
Wouldn't the
be-
potential equal the kinetic though? When it's when the potential that it has, when it equal and it would back out, wouldn't it equal the kinetic that it ended up with?
Also,
Yeah,
maybe,
so did you lose
But
it?
maybe it had
somewhere?
different kinetic too with the repel. You know,
Have you done this a lot
I
of
guess,
times
yeah.
and it came out to be,
Yeah, we did this like
you know,
for like 3 days.
So maybe your system, you couldn't get them close enough.
that
Because
it would-
I'm sure
yeah.
as you got closer, then
Yeah, I mean, we
Maybe.
could get within like a centimeter or two, but after that they'd connect, and then it might screw up some of our data. So, yeah, that's definitely something that would take a little more thought and trial and maybe a different approach to the experiment. But
Yep. Indie
so if
Lab
anybody
next
wants
year.
to pursue that, yeah.
Yeah,
go
next year. Let's wrap this up. So the purpose of this lab was to determine the magnetic strength of various magnets, and we did this by creating let's really wrap this up. So, you guys have any questions?
Matt had one?
Matt, you
Oh,
had
yeah.
a question?
Yeah, I was just wondering if you could explain like magnetic strength a little bit more, because I'm not really.
Okay. Okay, good question. So basically, what we said earlier, we said this equation can sort of be parallel to like the gravity equation,
Yeah.
which is like Fg equals big G m divided by r squared. So like you could essentially, it's like
Would it be like
it's like magnetic mass almost, or like
would it be like magnet like charge,
it's like the
like
strength.
for the electric?
or you could do.
What are the units?
That's kind of a way to look at it.
So it's like just
Dr. Sushi.
Yeah, is that mu naught?
Yes,
Yep.
right.
What is the value of mu naught?
5 times 10 negative 7.
Okay. Interesting that you have a 4 pi in there, isn't it?
It is very interesting.
Oh, so
So that
no, I don't know.
would just be divided by.
So you could just do r squared times f divided by 10 to the -7.
So times 10
4
to the
times 10 to the
7th.
7th, yeah.
Yeah, that's right.
That's interesting.
Yeah, I don't know if there's much more beyond that, but it's interesting.
But it's still being.
So it's a Newton for.
Oh, it's got units also. It's not just 4 pi times 10 to the -7. It's also got some units that
What
we
are
can
the
work out.
units of it, dude?
Oh, the units on magnetic charge? That
Well, I mean, like,
effective magnetic strength?
What would the magnetic strength be units of?
Well, they gave us those units and they're weird. I don't think you guys noticed that.
Yeah, they were amp meters.
Amp meters.
And that's one of the confusing things about some of those other equations was a lot of our research we did involved induced current and a lot of stuff we weren't sure about getting into. So, yeah, it's weird.
Go to
Well-
WashU, watch a lecture.
Any more questions?
I'm good.
Thank you, gentlemen.
Awesome. Please comment and rate.